I'm ready. Okay, super. Okay. Yeah, thank you everybody for coming. It means a lot that you're all here today to see my PhD defense about the electrochemical reduction of CO2 in acetonitrile on copper. So this has been a long time coming. I think I calculated this morning. It's 1,660 days since I started this PhD, so it's a lot of work that I'm going to have to defend today. But it's quite deep into the science, so I want to first introduce you guys with a layman's talk to kind of break it down into the core principles about what I was doing, so it's a bit more accessible to those of you who haven't done this for 4 years. Okay, so yeah, the problem with CO2. CO2 is increasingly becoming an issue. More and more emissions are being released, and you can see from the plot from NASA on the bottom right-hand side, we're at ridiculously high levels of CO2 in the atmosphere. And this is from industry, chemical industry, and burning of fossil fuels. Now, the reason this is an issue is because CO2 does this little dance, this little vibrational dance up here, which basically means we trap energy in our atmosphere, which heats up the world, which is bad news. So that has led to the ongoing climate crisis. Sorry, it's not very cheery, is it, to start? But you can see on the top-hand side, the red line is where we're currently headed with reference technology. And you can see each of these contributions, i.e. Nuclear, renewables, CCS, which stands for carbon capture and storage. And you can see how all of these things are going to have to come together if we want to try and limit the amount of warming as much as we can. On the left-hand side, this is a 2-degree scenario, so we'd warm the world by 2 degrees if we implemented all of these things together. And on the right-hand side, this is if we were overachievers and trying to go beyond a 2-degree scenario. But I want to make you aware of the green side, the green chunk, which is renewable energies, which are going to play an important role, and also the blue side, which is carbon capture and storage, where we're taking CO2 out of the atmosphere and storing it somewhere. So renewable energy is really good because it doesn't emit CO2, which is wonderful, but one of the main issues with it is that we have an uncontrollable supply. Essentially, we have a period of time where we have excess demand of renewable energy, i.e. everybody's at work and not dispersed across their houses, the sun's up in the sky, but we don't have enough, we have too much energy and don't have anything to do with it. So the question that scientists have asked is there a possibility to marry the two ideas together and use renewable energy to reduce the amount of CO2 in the atmosphere? this is the CO2 reduction reaction. CO2 reduction is a chemical term, but indeed it does reduce the amount of CO2 in the atmosphere also. So what we do essentially, to cut a long story short, is we take CO2, we bubble it through a cell, and we apply an electric current to it. And the electricity allows the CO2 to transform into useful things such as fuels, medicine, and plastics. But this is often done in water. And the issue of doing this in water is that we often have a parasitic side reaction where we make hydrogen instead. Now, we're already very good at making hydrogen by splitting water, so all of a sudden our very nice CO2 catalyst, which is very well designed to split CO2 into lovely products that we want, suddenly becomes a really bad hydrogen evolution catalyst. So the question we're asking is, how do we remove hydrogen from the equation? So this is a molecule of water, but what I studied is instead of using water as the electrolyte, we instead use this guy, who's called acetonitrile. Now, this one's quite nice because all of the protons on it are not acidic, which means that they're not released, which means they don't make hydrogen. It's impossible to make hydrogen this way. So instead of using water as our solution, we use acetonitrile, which completely stops the hydrogen evolution. So I want to take you down into my cell to describe each chapter now. So here we have my copper electrode. Somewhere far away from the copper electrode, we have our anode, but that doesn't really matter. Copper is where the work is done to turn CO2 into useful things. So let's zoom in here. I'm going to talk you through each of my chapters. So first off, we have chapter 2, which I was able to make nanostructured and shape-selective materials out of the copper by applying different fun cyclical thermograms, but that's beside the point. What I can do is basically turn the copper into either having lots and lots of little nanocubes on it, nanospheres, or these things called nanodendrites, which are really crazy-looking shapes like that. And we investigated how that changed the product selectivities. Moving on. We then, in chapter 3, looked at the size of the cation, which is about the salt, and investigated how that influenced the product selectivities. Chapter 4, we then said, what if we have different amounts of water in the electrolyte? How does that change product selectivities, going from a really dry condition to going to a very wet condition? Chapter 5, we took a bit of a detour, and we said, well, instead of building up from the bottom up, going from CO2 to these fantastic things, why don't we start with an interesting molecule and shove a CO2 molecule onto it to make things like medicines? And finally, we were left with a situation where we had lots and lots of different ideas about what was happening in our cell, but no strong way to really predict what was going to happen. So, for example, if we had one of these sort of situations where we had a small cation, but it was very dry, how do we really work out what's going to happen with the cell? Well, we're able to take such a system and program in a it's called a random forest model. It's a ensemble machine learning technique. But essentially, we're able to calculate what we would expect to be the most important variables in determining what makes each product. And that was my final chapter, chapter 6. So thank you all for listening. Hopefully it goes all right. I think it will. And enjoy. Thank you. We can talk, it's okay. We can talk for 5 minutes.
Dear guests, welcome to the special meeting of the Doctorate Board of the University of Amsterdam on the occasion of the PhD defense of Connor Deacon-Price on Wednesday, March 19, 2025. Dear candidate, would you please read aloud the first part of the formula before you?
By authority of the Rector Magnificus and the Doctorate Board of this university, I shall during this hour, in order to obtain the doctorate, publicly defend my thesis entitled The Electrochemical Reduction of CO2 in Acetonitrile on Copper. I entreat all those who wish to voice criticism of the contents of the thesis do so in a truthful and lucid manner, so as to provide an opportunity for an ordered exchange of views.
Thank you. I would like now to give the floor to the first opponent, Professor Andronescu, Electrochemical Catalysis, Chemical Technology, Universiteit Duisburg-Essen, which is in Germany. The floor is yours. And I would like to thank her for coming all the way from Duisburg-Essen to Amsterdam.
Thank you. Dear candidate, first of all, I would like to start by congratulating you for reaching this moment today here. I enjoy reading your work. It's an extensive study performed in a systematic way that allowed you to generate pertinent conclusions that, of course, are supported by the experimental data. And, of course, congratulations also on the publications you have until now. Good. I will start with some questions related to the experimental part. In chapter 2, you are using a reference electrode in a non-aqueous based electrolyte. Can you please explain what are the challenges associated with using a reference electrode in non-aqueous based electrolytes?
Dear opponent, thank you very much for your kind words regarding the thesis, and also I want to echo thank you for coming all this way for this event. Regarding your question on the use of reference electrodes, indeed it is difficult in organic electrolytes. In this instance, we use silver nitrate quite often as our pseudo-reference electrode. It's also important to understand that oftentimes you need to do a self-calibration with ferrocene-ferrocinium couples are oftentimes the commonly used one. This is useful when you have especially a dry solvent. Again, it depends on the solvent you're using in your cells. We did encounter issues in chapter 4 with ferrocene, in that it precipitated out because we had a wet solution, which made it very difficult to use the ferrocenium couple. Yeah, it's also important to be vigilant about reference electrode shifts and to make sure that indeed the potentials that you're reporting are the potentials. Yeah.
Thank you. Why you choose to work with dimensional stable anode as a counter electrode?
Okay, yeah. So in this case, we wanted to complete the current, and the anode choice was, I would say, secondary to the cathode. We have also in subsequent papers and chapters used platinum. I would like to also remind you that in this case, this was, we deemed acceptable because we're in separated cells. So
why dimensional stable anode? Because I can imagine that the platinum counter electrode is for a different reaction. So in chapter 2, what is your counter reaction?
The counter, okay, yeah. So this is yeah, a difficult question to answer because we haven't necessarily studied that side of the electrode, the electrolyte. So we would be expecting things like water splitting, I suppose, from that side of the reaction. But yeah, again, we weren't terribly concerned so long as the current was being completed because we were interested in the catholyte. Yeah. Okay,
thank you. Going forward, so we stay still in chapter 2, and you have several graphs where you have several cyclic voltammograms, and now if we are looking at the figure S1 that is at page 45, This has a typical shape in electrochemistry. Can you explain what processes can we identify based on this shape and based on the system that you investigated in this cycle?
To clarify, you're talking about the ferrocene.
Yes, so figure S1, so it's the page 45.
Yeah, so this is indeed how you can, these CVs are working out how we can adjust the cyclic voltammograms that you mentioned previously, earlier in the chapter before the appendix. What we are doing is we're scanning between two different potentials. You'll see that the current will rise and fall, which is related to oxidation reactions in the former case, in the latter case of a reduction reaction.
So,
yeah.
So if you are going on the anodic scan, so you see that you have a maximum, for example, if you look at figure C at 0.519 volt versus silver plus, and then you start to see a decay. This decay is due to what process?
Oh, so yeah, this is, so you're talking about the shape in that
yes,
it comes back down.
Yes, the shape of the CV.
Yeah, so this is actually related to the concentration at the interface of the electrode. Essentially what we're doing is we're reaching a certain point where it is saturated with the, well, if it's A to B, the B product of the reaction. So in this case, it would be ferrocenium. And then, of course, the current response drops because we have less of the reactant to cause the response to increase. So it's, yeah.
Okay, so it's a region where you start to see the mass transport limitation.
Exactly, mass transport limitation.
Good. Yeah. If we go then to the page 47, so we stay by the cyclic voltammograms. You have here the cyclic, so in figure S4, you have the cyclic voltammograms recorded 0.1 molar sodium hydroxide on the copper nanoparticles before and after. And you see some changes in the shape of the voltammogram. What is happening, or why you see these changes before and after electrolysis?
Yes, thank you for the question. So essentially the purpose of this CV is to identify the different facets which are being preferentially exposed during the, before the experiment in the production of the nanocubes. The first would be producing copper 100 facets, copper 111, and then there's copper-copper oxide redox going further to the right. Essentially what we're showing here is that after the reaction we have a reduction in the current response. We link this to the reduction of the roughness of the surface, and given that the response of the copper 100 is less so, it also indicates that we're losing some of those facets in operando. So after the experiment, we're losing the structure slightly.
Okay. Good. Now I have a question that I think can fit in many chapters, but let's say on chapter 3, you are using this, the Faradaic efficiency sometimes. What is Faradaic efficiency?
That's a good question, thank you. I like to think of Faradaic efficiency as a sort of product selectivity in regards to the electrons which are passing through the system. So to simply explain, we're counting the number of electrons which are passing through the system during a chronoamperometry. And then from the response of our chromatograms and the products that we're seeing, we can then work out, based on the concentration of those, how many electrons would be theoretically required to generate that much product, whatever it is. So theoretically, they should always hit 100% because we need to account for every single electron which is coming through. Of course, there's experimental errors which will never lead you to get quite to 100% exactly unless you're very lucky. So it's always a component of error. Yeah.
So when you say theoretically they need to reach 100%, whom are they? So what do you refer? So it's the Faradaic efficiency for a product, or what Faraday efficiencies, the Faradaic efficiency of whom needs to come to the 100%?
So the sum total of the products that we're seeing.
Okay. Good. So this is, it's important when we have multiple reactions or multiple products.
Yes.
And Good, then I am approaching my last question. So we are jumping one chapter and we reach chapter 5. So on page 127, you have several graphs. So let's say if we are looking at the figure 1b, you record the cyclic voltammograms in the presence of your substrate, benzaldehyde in this case, and CO2. So it's this full line green curve. Also in this case, can you explain, based on the cyclic voltammograms, what is happening when you change the potential?
So what is causing the response of
Yes.
the cyclic voltammograms as we sweep through the different potentials?
Mm-hmm.
Yeah. So of course it depends on the conditions that the cell is under. When we deaerate the system, you'll see that not much is really happening until very, very high potentials, because that's when we start to see decomposition of the electrolyte itself. You'll also often see that when you add CO2, it can also come earlier, which would indicate a CO2 reduction reaction occurring, and the substrate deaerated is just substrate responses, and CO2 is substrate and electrocarboxylation if it appears at an earlier stage. Yeah. Yeah.
Okay.
Okay, thank you.
Thank you.
Yeah.
The next opponent will be Dr. Kortlever, Group Leader Electrocatalysis, Delft University of Technology, and I would like to thank him for coming to Amsterdam.
Thank you. Dear candidate, also on my behalf, huge congratulations on a beautiful looking thesis, but also a scientifically very, very beautiful thesis. I read the thesis with lots of pleasure. There's a lot of nice science in there. It's also exemplified by the nice publications that you've put out. Of course, I do have some questions for you. And I would actually like to start my opposition in chapter 2. So I'm going to page 35, so figure 1, where you actually show these nice structures that you make via electrodeposition. And you characterize these structures solely, if I understand correctly, with electrochemical techniques. I was actually wondering, did you perform any other characterization techniques?
So we have the characterization, as you dear opponent, thank you very much for your very kind words. I'm getting carried away. Thank you for your kind words and also for coming all the way for the event. To answer your question, we have done the, as you mentioned, the scanning electron microscopy images to sort of get a macro scale idea of what we are seeing here. We have indeed the electrochemical responses. We did not carry out XPS or any other sort of experiments there. It would be nice to do so, I agree. But looking at other literature, the responses we get from the electrochemical, the CVs, that analysis was strong evidence that in combination with the microscopy that we had what we wanted to get.
Yeah, so basically what you conclude from the electrochemical measurements is that you have more copper 100 facets, right?
Yes.
Are you able to quantify to a certain extent how much copper 100 you would actually have more in comparison to the polycrystalline measurements?
Quantification is, I think, slightly more difficult to do so with these techniques. And I think that's when perhaps something like SPS might be a bit more useful. The reason I'm erring a little bit is because you can't really, when you're doing this technique, you're also increasing the roughness. So it's difficult to then normalize the increase in roughness, to then look at the CV to solely say, quantify the area, let's say, of your CV to work out how much copper 100 you have. Mm-hmm. So, yeah.
Yeah, I see your point, right? It's more difficult. I would also agree with you that it's more difficult to actually put a label on it. But then going to figure 3, that's on page 37, I was actually quite surprised that you have a 4-fold increase in your current if you look at the copper nanocube system versus the copper polycrystalline. Can you then solely correlate this to just an increase of copper 100 facets, or is there more at play?
So I want to actually disagree, because it's actually the nanocubes which have a reduced current on a per Yes, this is what you meant.
The other way,
Yeah.
the other way
Okay,
around,
yeah.
right? So you mentioned that the polycrystalline is fourfold more higher in hydrogen evolution activity.
If we consider this from a geometric, a electrochemical surface area perspective, then yes, that is true. So you can kind of consider this on a per atom basis. At least you've normalized the number of atoms. So what we do is, because we've increased the roughness when we do when we generate these nanostructured materials, we're increasing the roughness. That is accounted for by looking at the capacitative current in a separate experiment. Because the capacitative current is, it correlates with the roughness, you can do an experiment where you change the scan speed of your CVs, which increases your capacitative current. You can then work out a ratio between your nanocubes and your polycrystalline copper to work out a roughness factor. That roughness factor then accounts for the increase in current, so we're looking at exactly on a per facet basis almost what the actual work is being done by the material.
Yeah, but I can also imagine this double layer capacitance measurements that you do. There's a lot of debate in the literature how accurate those are, right? So I can also imagine that maybe you're underestimating or overestimating your surface. That might also give some fluctuations and some differences here, right? Would you agree, or would you still think that it's solely the copper one?
Yeah, and the other thing I do agree. The other thing I would like to add is when we're generating these nanocubes, nanospheres, nanodendrites, what have you, this is a wet chem approach, and it's hardly controlled. I would not describe the system as being controlled. So naturally, there's going to be some variation in the roughness factor that is achieved each time. So yes, that's another thing to consider. I do think they give a good idea about the increase in roughness. It definitely correlates strongly. But if you wanted very, very precise answers, then yeah, a different technique would be required, I would say. Yeah.
So maybe also tying into a previous question where you actually looked at the post-mortem CVs, right? And you say you get some morphology changes after the 19 minutes electrolysis. Yep. So does that? I could not find it in your chapter. But do you also see variations of your currents over time then as well? Moving more towards a polycrystalline system? Yes,
so it's very rare in any of these systems that we study that the chronoamperometry provides a stable current throughout. It's a dynamic system, let's say, to say the least, especially with copper. Copper is a very dynamic material and problematic from that point of view. Mm-hmm. Sorry. Would you like to...
No, I think okay. Maybe let's move on.
Sure.
Because I also had a question later on in the same chapter in the FTIR analysis. You actually you mentioned that you see some degradation of your acetonitrile, right? And I was wondering how much does this actually, or could it contribute to some of the Faraday efficiencies that you're seeing in Figure 6 that's on page 37? Are there any degradation products that would actually lead to products that you would also see from CO2 electrolysis?
Yes, you would. If we're seeing in the IR that we are noticing bands which are related to that of acetamide, or sometimes you see free aminocrotonitrile, which is another decomposition product, then yes, that must be accounted for within the Faradaic efficiency because it doesn't discriminate between CO2 reduction reactions. It's just a net total. That is provided that this decomposition is occurring at the cathode.
Sure, but then that you would see as a loss in your Faraday efficiency, right? So the decomposition.
Well, the Faraday...
What I'm hinting at is that are there any reduction products from your acetonitrile that you could also label as potential CO2 reduction products like CO or formate or that you actually now link to CO2 electrolysis, but actually are stemming from...
I see. So you're asserting that perhaps some of the products that we're assigning to CO2 reduction reaction are instead coming from that of acetonitrile instead. Is it possible? Yes. In my personal opinion, I do not think it is likely. At some point, I believe in chapter 3, we see acetate being formed. I believe that's more likely, as it is not accounted for within what is understood to be the aprotic mechanism to generate these CO2 reduction reaction products. That's one of the nice things about aprotic CO2 reduction, in that the product scope is actually very limited. There's only really 4 different CO2 reduction reaction products that can be formed. So it's a possibility, yes, but you would need to do some more experiments for sure to be able to determine the source of the product.
Okay, clear. In view of time, I would like to switch to chapter 3.
Please.
Let's have a look. And in chapter 3, you, on page 58, you show the everyday efficiencies to all of these different products. And I was actually quite intrigued that you see so much oxalate with the TEA, yep, and not with the TPA and the TBA. And I'm not sure if I'm fully convinced by your description on why you see oxalate there, but not in the longer alkyl chain. So can you speculate a bit on what is the reason behind this oxalate selectivity?
So yeah, thank you for the question. We assert that this is coming from a relation to the hydrophobic hydration of the cations, in that as you increase the chain length of the cation, you necessarily increase the amount of water which is at the interface. So local water concentrations increase as you increase the chain length of the cation. Oxalate is a solely aprotic product. It requires that 2 CO2 radicals meet and terminate with one another to generate the oxalate. So it's very sensitive to the amount of water which is in the system. And we can also verify that the bulk water, at least, in these systems are very close to one another and very, very low. So yes, you could perhaps argue that this is an electrostatic route that is causing this, so a specific absorption to the CO2 to stabilize it in different ways. I think that's unlikely because of the conformation which the tetraalkyl ammonium cations will take when they arrive at the cathode. When they come close to the negative bias of your cathode, there's a conformational shift which pushes the alkyl chains out of the way, which then you're just left with your nitrogen point charge, the N+, at the surface. So electrostatically, talking about the stabilization that would provide, it wouldn't be too different, in my view, because we're all using the same cation. This is different in aqueous, but if you have lithium or cesium, of course, these are essentially point charges, right? Mm-hmm. So these have quite a strong influence, at least from an electrostatic point of view. But because nitrogen, they're all nitrogen, N+ species, yeah, this is kind of the way we went down this different road, this hydration route. Yeah.
Thank you. The opposition will be continued by Professor Alarcón, Lladó, 3D Photovoltaics, AMOL of University of Amsterdam.
Thank you. Dear candidate, congratulations also for this thesis. It is a very thorough work, I would say, and also in a relatively not infant but not so much explored world in electrochemistry. And I learned a lot about solvents that are not water, so thank you for this. I would like to start with some technical questions. So for the sake of looking at a page, let's go to page 40. There's this figure, right, with spectra, FTIR spectra. And I was wondering if you could very briefly explain a little bit what is the experimental setup, like the configuration of your measurement.
Dear opponent, thank you very much for your kind words about the thesis and also for bringing up my favorite technique in the PhD. I love in situ FTIR. It's a very beautiful and elegant technique. So essentially what we're doing here is we're creating a thin layer configuration. So you can imagine that if you fire your IR beam at your sample, it has to travel through a significant amount of solvent molecules, if you could imagine the normal setup, let's say, which completely destroy any sensitivity of your surface. The thin layer configuration sort of aids the situation somewhat, in that we're pushing our electrode very, very close to a prism, so we can just look as closely as we can at the surface only. So that's how we're able to look at the surface effects in the IR. So that's, I suppose, discussing the configuration, the technical side of the IR.
Yeah, great. And then that brings me then maybe to my next question. How can you be sure that this thin layer configuration is equivalent to your regular electrochemical experiment in a regular electrochemical cell?
Could you repeat the question, sorry?
So basically you have this thin layer configuration, a very thin layer of solvent, where you could encounter also some mass transfer problems, just to say one of the few things that is different from the traditional electrochemical experiment in a traditional electrochemical cell.
So you're right, there is indeed definitely a mass transport limitation influence here. The way that this setup is done is that we first initially run a chronoamperometry at a potential where, informed by our CVs, that there should be no current. So we kind of have a equilibrium point where we suddenly at one point have no change in the current over time. Sometimes this takes up to like half an hour to try and get a very, very stable current. At that point, we're then happy that the system is equilibrated. And then we then change the potential, subsequently taking scans. And the change in potential is what shows you when things are consumed and when things are gained, and the position and shape of these bands informs you what exactly that is. Yeah.
That's clear. Maybe now still talking about the FTIR. So if you look at the spectra, this is absorbance, as you call it, right? And you have peaks in a negative direction and peaks in a positive direction. Can you very briefly explain how do we interpret this?
Yeah, so we're taking a background spectra and it's subtractive. So the chronoamperometry I mentioned earlier, we take a scan at that position. We take multiple scans at that position to ensure that there's absolutely no change happening anymore. We then use that reference as our point to then observe any change. So you can imagine if you take that background reference scan and you then take a scan immediately after at the same potential, you should see a straight line or a very, very, very low absorbance on that thing because nothing has changed since. As you then change the potential, you're changing the electrochemical environment at the cathode, which can infer changes in the at the Helmholtz plane. So that's how we're able to determine that the surface is changing because nothing else is dynamic in that system.
So basically, you always choose the same potential for your reference scan?
It depends on the CV. So the CV will inform where there is no potential, where there is no current being involved, because we don't want to see any current. We want to have a neutral point, right? I suppose if you want to talk theoretically, I guess you could do it at -2 and then go to -2.1 and you should see a change, but it's a reference potential where there is no current and you see the full story as you scan through your potential range of your CV, and then you can identify where each thing's happening across the CV.
That's very clear now, thank you. I would like to move on to another technical point, which is related to the Faraday efficiency. There was already some discussion about this, so I'm very excited that you mentioned, sometimes you expect 100, but maybe we measure less than that. What I was triggered by, and particularly from my physics background, is that whenever you have something as an efficiency that is above 100, that's some sort of a red flag or a ringing bell. And if I look at page 58, for instance, figure 3, it looks to me like there is something above 100. Yes. Can you care to explain?
So, what is important is to take multiple measurements and then using, of course, again, I'll echo what I said previously, there is experimental error, but the purpose of this is to take multiple different experiments at these and then take an average of these. So you'll notice that there are error bars in these often, and so long as the error bars overall bring you below the 100% efficiency, you know that it is feasible. Thankfully, our Faraday efficiencies don't often go over 100%. It's perhaps better to have a lower amount because at least you're not accounting for things and you can explain that. Over 100%, I agree, theoretically should not be able to occur. But when you consider that there is experimental error, we are measuring chromatograms to try and work out exactly where each electron has gone. That's difficult. So some fluctuation is expected as well.
Well, thank you. That gives me some rest. I think my time is up. Thanks.
Correct. The next opponent will be Professor Reek, Supramolecular Chemistry van 't Hoff Institute for Molecular Sciences, University of Amsterdam.
Dear candidate, I also would like to congratulate you with a very beautiful thesis. The cover is very nice, there are many nice pictures, and also the content I really liked. I also have a few questions for you on chapter 5 and chapter 6, so I would like to start on chapter 5, where on page 127 you have the electrograms, and they explain, let's say, the mechanisms, pathway 1 and 2, in scheme 2 a few pages before. And if I look at the green curve, then I fully understand. So if you look at the dotted line, this is the substrate reduction in absence of CO2, and then you reduce it, and in presence of CO2, it reacts with CO2, so it can absorb another electron, so the current is higher. So I fully understand that, and also your text around it. But then if I look at figure A with the benzyl bromide, yes, then I see a current that is shifted with respect to the substrate and the nitrogen, and it is shifted with respect to the CO2 reduction. So I do not understand your explanation on why this is a support for pathway 1. I don't understand this shift at all. Could you explain it to me?
Your query, dear opponent, thank you very much for your kind words, especially regarding the content of the thesis. So your question is regarding, in this case specifically benzyl bromide, that's what we're looking at. And you're wondering the potential that we've picked for the Faraday coefficiencies?
No,
is this the question?
What I'm wondering is that the reduction is shifted more positively in the presence of CO2. Mm-hmm. So the green curve, you understand, it's very logic, but for benzyl bromide, the current is shifted with respect to the nitrogen, and also the CO2 reduction is shifted. Mm-hmm. So I cannot see any correlation to any of the either the two pathways that you described in scheme 2.
So again, I have to qualify. You're talking about the CO2 and nitrogen with or without the substrate introduced to the system?
Yeah, so I'm looking at the orange curve.
Yeah.
It's substrate plus CO2,
yeah.
that potential.
Yeah.
Yeah? And if you compare that to the same electrogram under nitrogen, then it's positively shifted.
Yes.
Yeah. And if you compare it to the CO2, it's also positively shifted.
Yes.
Why is that?
So, yes, thank you for the good question. You can tell it's good because I had to qualify a lot of things to answer it. So, essentially, the strength of the CV is it's an ensemble, right? If you look at a single CV, it's not very useful. You have to cross-compare to understand what's happening. So we can see that the CO2 reduction is occurring before the degradation of the acetonitrile, 0.1. This is dotted black versus solid black. We can also see that when we just have our substrate and no CO2 to react, it's occurring in sort of a middling point here in the CV. And then when we add CO2, it then shifts even further back. You agree so far? Yeah?
Yeah.
Okay, so if the route were to proceed through an activated CO2 molecule first, as we described in the scheme earlier, this would necessarily have to occur once we have the activation of CO2 possible, which takes place much, much later in the CV, which therefore suggests that it is indeed the substrate which is accepting the initial electron transfer to then react with the CO2.
I love your argument, but I can use the same argument for the substrate, and therefore I was puzzled. But I think we will not come to a conclusion on this aspect. So I would like to go to chapter 6 to page 153. And I first would like to ask an elementary question, and that is, do you know how current, potential, and resistance are correlated?
Yes. So you're talking about the big three that we see, essentially, right? The big three factors.
So if you look at high school, elementary high school knowledge, So are current, potential, and resistance correlated?
Yes.
Yes.
The equals IR, yes, they are
So,
very much
so this
correlated.
means that you also expect that current density, applied potential, and cathode conductivity are correlated.
Yes.
And if I look at figure 5 on the oxalate, then I was very surprised that you see a dependency on applied potential and on cathode conductivity, but not on current density, while I think they are correlated. So why don't you see also dependency on current density here?
Yes, that's a fantastic question. Thank you. So clearly, at least within the viewpoint of the potential and the current, we have a very strong correlation that essentially when you increase one, the other should increase as well. The resistance is, I would say, related to the cathode conductivity. I don't think it is the same thing as just the resistance in the sense of V equals IR. I do agree, though, that, and we do indeed see, if you go back to figure 4, that the applied potential and the current density are linked. The way that this is calculated is that we're taking a very, very large data set from the literature, and we're recording the noted potential and the current density for each of those, and then we're asking the random forest model to work out which parameter is most strongly indicative to creating each product. So, yeah, that's why.
I have a slightly different interpretation, but
Okay.
in view of the time, I won't elaborate on that.
Okay.
So thank you for your
Thank you.
Thank you. Your presentation will be continued by Professor Meijer, Computational Chemistry, Van 't Hoff Institute for Molecular Sciences, University of Amsterdam.
Dear candidate, a beautiful thesis has been said, also very interesting content, and indeed, you probably agree with me, good content should be embedded in some nice environment, and you did so with a nice picture for every chapter. Also, I like this field because it's chemistry, but also you need like physical chemistry and physics to really fully understand everything that is going on there. So this is a nice interdisciplinary area. I'm a bit I'm not an expert, so my questions will be, say, from someone who's on a distance, and I'd like to start with, I think, maybe a very simple one, which is in the introduction, you give a sketch of the system, which is page 5, and this is, the electric double layer. You have the surface, where most of the chemistry happens, or near the surface it might happen, and there is a solution with cations, anions, solvent, and clearly this is a sketch, and the real system is probably a bit different. And so could you explain to me what are the important differences between the things you are using in your experiments, the kind of systems, and the very nice idealized system you see here in this picture? And maybe those aspects that actually are, say, maybe relevant for how the system works.
Okay. Dear opponent, thank you very much for your kind words and for your nice question. Indeed, the sketch is an idealized view of what the system will look like. I think in general, it's relatively representative, although I would like to, in context of the tetraalkyl ammonium cations, that the hydration of those is different to that most point charge species, which is what this is indicating in an aqueous system. We also have two different solvent molecules, and that we have acetonitrile and water. We discussed that in chapter 4, where we do some computational studies to have a look at how the acetonitrile and water behaves, and how that explains our results, and essentially why our system is so sensitive to water when we have a relatively low volume percentage of it. Yes. To clarify, essentially the water has a much more preferential approach towards the cathode, and it isn't inhibited by the acetonitrile at all. So, yeah.
Yes, thank you. Thank you. There might also be other things, but might discuss this later. Then I have a question on chapter 3, where you look at the effect of cations, a particular set of cations, on the electrochemical CO2 reduction. And so one of the aspects you note, and you also use in explanation, is like the presence of water. and the like the hydration of the cations playing a role and driving it to seeing more hydrogen or less hydrogen. And my question is maybe motivated by a recent thing I saw in homogeneous catalysis, where also cations and CO2 reduction play a role, the cations. And there one of the aspects was that the presence of cation does something to the stability of the adsorbed CO2, which is a CO2 minus, and an ion, CO2 minus, and a cation, some positive ion. They might interact, and this might affect the actual stability of reactants and products. And this, I did not see this written in your chapter, and this might not be important at all because of the nature of the cations you have. But could this be also an aspect that could play a role in what you saw in terms of products?
Yes, it could be, and I suspect that it is in some way describing the product selectivities. Again, I will discuss the conformation of these tetraalkyl species, which I think you expected, in that we have the same cation, the point charge is the same across the tetraalkyl ammonium species. So to look at such a difference in the product scope and this product selectivity just by changing those species whilst controlling for the water concentrations, it simply can't explain the breadth of results that we see, which is why we then discuss the hydration being as more important.
Yes.
Yeah.
And so like water plays a role, you indicated it also in the different answers you gave. And so I can imagine also like how the water orients or rearranges as function of the distance to the surface might play a role. That might also be something that is in chapter 4. And so it would be interesting to actually be able to probe the organization of the water perpendicular to the surface, how this is arranged. And I was wondering if there is like advanced experimental techniques that actually can do this. And you might
in a sense,
can we have a short answer?
In a sense, this is already in the thesis.
Yes.
If you look at the IR of chapter 4, we can see that there's different vibrational modes in which the water is absorbed, which either has a dangling OH group, which describes in the hydration shell, or bend and libration, which describes a hydrogen bonded network.
Yep. Okay, thank you for your answer.
Thank you.
Thank you. The final opponent will be Professor Noël, Flow Chemistry, Van 't Hoff Institute for Molecular Sciences, University of Amsterdam.
Oh, yeah, dear candidate, I also had the pleasure to read your thesis, and since time is running out, I'm going to immediately dive into the questions. So you always saturated your solutions with CO2, right? And I was wondering, what's the conversion of the CO2 in the liquid?
What the conversion of the CO2
yeah,
is?
how much CO2 do you actually convert?
Oh, yeah. Dear opponent, thank you. If you're talking about the amount of CO2 that we put into the system, taking that as one large value and then working out exactly how much of that has been converted, that was not calculated for. We're only saturating the system, especially in the sense of the online GC results. We're simply pumping CO2 through the system, and it has an outgas, and it's coming out of the system. So we're essentially just looking at CO2 which is dissolved within the electrolyte itself and the conversion thereof of that CO2. If I were to guess an answer, it would be extremely low because it's passing through the system again and again. If you were to try and design an industrial system, perhaps you'd try to recycle the outgas. Yeah.
That's also what I thought. So, and most people in the community also dodged that question, maybe less elegantly like you did. But if we want to solve the CO2 problem, right, we need to convert large amounts, and so. How do you see that going on? Because how much is actually dissolved in the solvent? And so how much of the problem are we actually solving?
Yes, I agree that that is a challenge to be tackled. So in acetonitrile, this is one of the benefits of using acetonitrile, other than that we're avoiding the hydrogen evolution by limiting the amount of hydrogen there. Is that we have about 8 times increase in the solubility of CO2 within the electrolyte compared to water. Yes, that's good, but it is still very low. We're still on the I think, 300 ppm range. So if you were to try to address this industrially, You could perhaps look into a pressurized system and indeed a recycling of the CO2, perhaps a flow cell. Who knows?
Flow is always the answer, in my opinion. But so the question is like, what is then needed, right, to get to that final conclusion that we want as a society also? Because I think CO2 is a very challenging problem. It's also almost inert. And so if we really want to solve this, like, what would you, let's say you get 2 million euro, what would be the first thing that you would try to do in this case to actually start solving the CO2 problem? So what are the remaining bottlenecks in the field? Mm-hmm. Is it the conversion? Is it reactor engineering? Is it the electrochemistry? Where would you put your money on?
I think the reactor engineering is probably the biggest issue so far. Indeed, the point of this study was to kind of get a systematic understanding of the fundamentals, but indeed a reactor design, I think, is required if you want to address the conversion issue.
Thank you very much.
Thank you. This concludes the period of defense and opposition. I now request you to read aloud the second part of the formula.
Having concluded the defense of my thesis and pending the decision of the Doctorate Committee, I would like to express my thanks to my highly esteemed supervisors and co-supervisors, in particular to those who have brought forward their criticisms and to all who have attended this ceremony.
Thank you. The committee will now retire for deliberations.
I didn't feel like I rushed it.
Esteemed candidate, after due consideration of the thesis you have submitted, we have decided to grant you the doctoral degree. Professor Rothenberg is authorized to confer this dignity to you in the customary fashion.
Most gladly do I accept the task assigned to me by the Rector Magnificus of the University. By virtue of the power conferred on us by law, and in accordance with the decision of the Doctorate Board of the University of Amsterdam, I hereby confer upon you, Connor Deacon-Price, the degree of doctor, and grant you all the rights pertaining thereto by law or custom. In evidence thereof, you will receive the degree certificate signed by the rector and the supervisor and confirmed with the great seal of the university. Do you promise to uphold the principles of academic integrity, honesty, diligence, transparency, independence, and accountability in your work at all times?
Yes, I promise to do so.
Then regard the obtained dignity as an honor and a privilege, and never forget the attendant responsibilities which you now bear towards science and society. Having fulfilled the task assigned to me, I have the honor of being the first to address you as doctor and to congratulate you with the dignity conferred on you. Dr. Connor, congratulations.
Dear Dr. Deacon-Price, dear Connor, congratulations on achieving your PhD degree. Today is a special day for both of us. As you become a doctor, I celebrate guiding my first PhD student to this milestone. Thank you. I'd like to extend my acknowledgments to the committee members, Professor Gadi Rothenberg, Dr. Corina Andronescu, Dr. Ruud Kortlever, and Professors Joost, Reek, Timothy Noël, Evert, Meijer, and Esther Alarcón for their invaluable contribution and discussion today. Let's go back to 2020, during the peak of COVID, when we first met at Boulder. It was a cold day, but the chill didn't dampen our spirits. You were a young man looking for a PhD position, and despite the doubting prospect of joining a young PI with no established infrastructure, you accepted the challenge. Our initial project was to explore the electrocarboxylation reaction, but first we needed to tackle the complex behavior of the electrochemical CO2 reduction reaction in organic solvent. As you noted in your thesis, we started our electrochemical lab from scratch, tuning bare bones into the powerhouse as you mentioned. In the beginning, we did experiments together, but I felt something was missing, what I like to call as the good hands for electrochemistry. That was when Mark very kindly opened his lab in Leiden to you. You were traveling back and forth between Amsterdam and Leiden for weeks, possible even months, gaining invaluable experience alongside postdoc and PhD students like Alison Marks, Rafael Vols, and Stefan. Back in Amsterdam, we were fortunate to welcome our first postdoc, who you likely to refer as an angel, Dr. Cassia Santana. The two of you worked so hard on synthesizing copper nanocubes to investigate their activity during CO2 reduction in organic solvent, leading to our first publication in the Journal of Physical Chemistry C. During the revisions of this paper, we encountered the ever-persistent referee number 2, who bombarded us with 27 questions about cations in aqueous solvents, a topic that we were even not discussing. What this referee did not know was that we were already exploring how different tetraalkyl ammonium cations interact at the electrode interface in organic solvent. By then, you had taken under your wings your first master student, Louis. What you teaching him with such passion was a joy. After 357 cyclic voltammograms, I never more will forget those numbers in my life, and numerous online GC analysis, your remarkable work was published in ACS Catalysis. Our fascination with the electrochemical interface in organic solvent was growing up and up, especially with how even a few ppm of residual water could impact our studies. To understand how water competes with the adsorption of active sites on copper electrodes, your second master student, Nina, who now will follow up this project, began investigating the effect of water content during CO2 reduction reaction. In collaboration with Ashik, Ping, and Professor Evert Meijer, we demonstrated that water was preferentially adsorbed over the acetonitrile molecules, culminating in a beautiful publication in CanCat. Numbers always intrigued you. We saw during your presentation you talking about 1,000 days and something. And luckily, your next master student, Alexandra, shared your enthusiasm. Together, you delved into 261 CO2 reduction reaction examples from the past 50 years in 2 months, I have to say, analyzing 9 different parameters. That's crazy. This extensive study, conducted in collaboration with Professor Gadi and Professor Wolf, resulted in another insightful publication in CanPhysCan. As your PhD journey was getting close to its end, we went back to the initial project about electrocarboxylation. I knew it seemed overwhelming, and you might have felt like killing me. But I entrusted this task to you because I knew you could handle it. Alongside Eleni, another brilliant master student in our group, and under the co-supervision of DJ, who, although no longer with us, continued to support us in this project, you wrapped up your thesis with a compelling history about the copper electrode and its potential for electrochemical CO2 valorization in organic solvent. Connor, I know it wasn't always easy. There were many meetings and discussions, and sometimes I was really worried about whether you were still happy and content with your PhD and your project. It was tough, there were tears. Blood was a bit too much, I have to say. But look at what you have achieved at scientifically, but even more important, at personal level. The quality of your thesis is outstanding, and your research has significantly advanced our understanding in organic solvent. There is still a lot to learn and discover, but rest assured, you have kicked the ball rolling, and I couldn't be prouder of you. Thank you from the bottom of my heart for your hard work and everything you have done for our group. I also would like to extend my congratulations and thanks to your family, your parents, your sister, that I don't know if it's here, and your lovely girlfriend, Lot. Without their support, none of this would have been possible. I wish you all the best in your future, success in your new job now back in UK, and I hope you enjoy this day as much as I do.
Thank you. It gives me a great pleasure, most learned scholar, to congratulate you also on behalf of the Doctorate Board of the University of Amsterdam on this newly acquired honor. And I hereby declare the ceremony closed.